given this function, given a point where we at least know x equals -1. Let's start by finding the derivative of the function. Okay, if we're going to find the derivative of the function, the way the function is spelled out in terms of y here, we could say y prime for our derivative is going to equal. Think about the rules that we have to play with and the rule that would apply here. This is a quotient for a function, so we'd apply our quotient rule. And applying the quotient rule, you take the derivative of the top first. Derivative of a constant we know is 0. You multiply to the bottom, which is just x plus 3. You subtract the top piece as is, 2, times the derivative of the bottom. So on the bottom we see this x plus 3. We start with the x term. Got a coefficient of 1 there, so we know we're going to have a 1 for that term because the x is just going to drop. And then we got another constant there, 3, that's going to go to 0, so derivative of the bottom is just 1. This is all going to be over the bottom part, x plus 3 squared. Now normally as we take derivatives for what we've talked about so far, we leave that in an unsimplified form. But because this is going to have an application for us, because we're going to find an equation of a tangent line here, we should go ahead and clean this up. And really cleaning this up is not going to be too bad because you've got 0 times a quantity here. That's all gone. You've got -2 times 1 left, so it's going to be -2 over quantity of x plus 3 squared. So where this derivative has use for us, it's basically serving as a formula to help us find two things. We can find the slope of the tangent line with it. We can find a velocity with it. So here, let's find the slope. To find the slope, if this is serving as a formula, well, I look at what this expression is comprised of. It's comprised of some x values, so I need an x value to plug in. That's where this given x value up here comes in handy. I take -1, I plug in. So as I plug this in for notation purposes, since I'm using the derivative here and that's y prime, I could say I'm plugging -1 into that, so it'd be y prime of -1. That's going to equal, substitute -1 in the place of x, it'd be -2 over, if I write it all out, -1 plus 3 is a quantity squared. So you do that calculation, you got -2 over. This would be 2 squared, so 4. -2/4 would be -1/2. There's your slope. Now bringing this all together and forming an actual equation of a tangent line. Well, the equation of the tangent line that's passing through this point where x is -1 on this curve. Now think about what I need. I need two things, right? If I'm going to put this in point-slope form, I need a point, I need a slope. So I got my slope, and I got part of a point up here. I know what the x-coordinate is in this point. But how am I going to find the y-coordinate? Okay, you're going to plug it into the original function. You got another formula up here to figure out what y is, right? Y equals 2 over x plus 3. So take -1. Replace that x. You got 2 over -1 plus 3. That's 2 over 2. This point is going to be -1, 1. So equation in point slope form is going to read as y minus the y value at the point, which is 1, equals our slope, which we found to be -1/2, times the quantity, x minus the x value at the point. We're subtracting a -1 there, so it's going to be x plus 1. There's our equation that represents the tangent line. Okay, now the illustration, the visual appreciation here. What I would do to piece this all together, I would like to represent on a graph this function here as well as this line here, and show how this line is passing through just this one point on this curve. So how I'm going to do that? Yeah, I'd plug into the calculator, probably get a sense of what this looks like by looking at the calculator graph, maybe approximating some of the intercepts and using those as key points to plot this out. But I would also take this point of tangency at -1, 1 and maybe start there in terms of plotting out not only the function but the line itself, because we know both of those are going to come together at that point. So if I plot that point of tangency at -1, 1, there's that point. We know both the curve and the line will pass through that. Now let's go to the calculator and let's plug in the original function. Right, so there's the graph of the original function. Few key points or key things we might want to plot out here. We could see that this graph is going through the y-axis right around where y is going to be 1, so that could be a key point that we could use. We also see there's a vertical asymptote right here at -3. So probably want to put that in there and show how the graph surrounds that asymptote. So if I come back over here, like I said, it's passing through right around where y is 1, right there on the y-axis. There is a vertical asymptote over here where x is -3. And the rest of the curve, how it surrounded that asymptote, well, it kind of looked a little something like this, didn't it? It comes down through these 2 points here and kind of rides the axis out from there. So I'd say that's a reasonable sketch of the original curve. Now if we put the tangent line in there, since we already have our point of tangency mapped out right here at this point, you could take your equation, you could put it in slope-intercept form and then graph off of that. But since you know the slope is going to be the same for any of the points on this line, and you know this is going to be one of the points on this line, then I just take this slope of -1/2, count off from this point, using that slope to find a secondary point. So if I do that, counting from this point, I'd go down 1 and then 2 to the right. That'd be a fair secondary point. Now we can sketch our tangent line through those 2 points. I'd say that's a pretty good sketch of the graph.